Let's see now the effect of temperature on metals, semiconductors and insulators separately. First of all, that for the metals. You see, metals have very high value of electron density, that is round about 10 to the power 28 or 10 to the power 29 per meter cube. So, very high value. The specific resistance for them is that of the order of 10 to the power minus 8 ohm meter to 10 to the power minus 6 ohm meter. And alpha is positive. Positive, its value is given 10 to the power minus 3 per Kelvin. Why this alpha positive, that we have to see? You see, this is M. We have written that overall rho depends in particular on n and tau. You see, tau is equal to lambda upon Vrms. When we increase the temperature according to this relation, root 3 kT by m, T increases, T increased, RMS velocity of free electrons will increase. And when the RMS velocity increases, tau is going to decrease. Tau, that is relaxation time, which is the time interval between two successive collisions of free electron. When tau will decrease, you see, rho will increase. So, if you combine the two results, you are increasing the temperature, and that entails the increase in specific resistance. That's why it is said that alpha is positive for the metals, confirming that when you increase the temperature, specific resistance, or even that way you could say resistance of metal increases. RT equal to R0, 1 plus alpha T. But you see, for most of the metals, practically we find alpha comes out to be of this order. If we put this value, we put this value in the relation RT equal to R0, 1 plus alpha T, 1 plus alpha T. Here, blank space, it should be written as alpha. There I am writing 1 upon 273. So, what we find here, 273 plus T upon 273. See, 273 plus temperature in degrees Celsius, that becomes the temperature in Kelvin. Now, it's a very important result to see RT. This is proportional to absolute temperature. This is exactly same as in the case of gases, Charles' law and law of pressure. What we find here is that the resistance is directly proportional to absolute temperature. Mind, it's absolute temperature, it's not the temperature on Celsius or Fahrenheit scale. So, between resistance and temperature, the relation, it appears it should be straight line exactly. But this relation, this value is not common and equal for all. It is variable. I told you it's on the average, it is found to be of this order. So, actually what happens with the temperature, resistance increases, and when the temperature starts decreasing, all of a sudden at a particular temperature, what we find, that temperature suddenly reduces to 0. Resistance suddenly reduces to 0, and 0 resistance, superconductor. When the resistance becomes 0, the metal has been converted into superconductor. This particular temperature at which superconductivity takes place, this is known as transition temperature. Transition temperature is mostly very, very low, but now the efforts are on to find the superconductivity even at higher temperature. So far we could be successful, we have been successful in finding superconductivity up to the limit of 125 Kelvin. You see, cryotron is a type of switch, electronic switch, that is based on the principle of superconductivity. Magnetic trains, you might have heard the name. Japan has been successful in running magnetic trains. Magnetic trains are running on the principle of this superconductivity itself. For alloys, you see alpha is positive but very low. For alloys, that is combination of metals like constantan, manganese, nichrome. For alloys, since alpha is low and positive, a small value of alpha means there is not the greater variation with the temperature. Resistance almost appears constant. Resistance will maintain its value constant in the lab. That's why we prefer for the practical labs in physics, the resistance wires are chosen always that of constantan and manganese. You see, if we plot the graph between V and I, Vi are proportional, this theta, tan theta is going to be equal to R. V upon I is equal to R. And you have seen here that R depends on temperature. That means this slope will give you the temperature also. You plot the graph between V and I, this slope is going to give you the idea of the concerned temperature. That means you are having two graphs, and for one particular graph the slope is greater. It will clarify that the temperature concerned is greater. Now for semiconductors. For semiconductor, I told you already that N is not very high. Covalent bonds broken, N increases, and when N increases, rho will decrease. That means for semiconductors like silicon, germanium, when temperature increases, the resistance or the specific resistance will decrease. That's why it is said that alpha is negative. The values are given electron density of the order of 10 to the power 16 per meter cube, specific resistance 10 to the power 3, and this value of alpha minus 10 to the power minus 3 per Kelvin. When I told you temperature increases, N increases, rho decreases, so alpha is negative. That means you go on reducing the temperature, the resistance will go on increasing, and we might say with confidence that at absolute zero, or you might say 0 Kelvin, the semiconductors will start behaving like perfect insulator. It's given over here. But here one thing you must remember, that conductivity is possible in semiconductors because of hole and free electrons both. Whereas in the case of metals, the conductivity is only due to free electrons. So here for conductivity, we are going to use the relation sigma equal to N E mu. It was basically for metals, N E mu. Mu used to be the mobility for electron, but now it's going to be that for electron, and again that for the holes. Insulators, N is almost 0, specific resistance is very high, and the examples are given here. For mica, alpha is this thing, minus 50, 10 to the power minus 3 per Kelvin. Rho is order here, 10 to the power 16 ohm meter. For particular mica, it's given separately. With the increase in temperature here also, we can say that the resistance will decrease, but it's never going to be 0, as in the case of semiconductor. Finally, this very important result has been given for thermal current and electric current. The ratio of conductivity for conductor and insulator that has been given 10 to the power, this is 22, and 10 to the power 13. This is conductivity for conductors and conductivity for insulator. This ratio is given. Listen again, the conductivity, specific conductivity for conductor, specific conductivity for insulator. Ratio is of this order for electric current, and that for thermal current, this ratio comes out to be 10 to the power 13.